Chapter 3, Metals and Non-Metals. Classification of elements.
In our daily life, we come across many objects and substances around us. They are all made from elements. Let us collect some objects or substances from our surroundings and list down the main elements present in them. Copper wire has copper. Silver box has silver. Aluminium can is made of aluminium. Coal powder has carbon. Sulfur powder has sulfur. A pencil with graphite core has graphite. Take two baskets and label them as A and B. Now, observe this collection of objects or substances and carefully pick the objects which are hard and have a shining surface. Yes, you have done it right. Copper wire, silver box, and aluminium can are hard and lustrous. That is, they have a shining surface. Graphite core also has a shiny surface but is brittle and not hard. So, we will not pick it up. Now, put these objects in the basket A. Observe the remaining objects. Well, sulfur powder and coal powder are soft and do not have a shining surface. Put these objects in the basket B. Here, we arrive at the classification of substances. We know that substances are made up of elements. Elements can be broadly classified into two groups, depending on their characteristic properties. Metals and non-metals. Generally, metals are hard and lustrous. Now, can you tell which basket has objects made from metals? The basket A has metals and the basket B has non-metals. Some of the examples of metals are aluminium, copper, iron, lead, tin, zinc, sodium, potassium, magnesium, calcium, mercury, gold, silver, and platinum. Carbon, nitrogen, oxygen, chlorine, sulfur, graphite, and diamond are examples of non-metals.
Apart from metals and non-metals, there is one more class called metalloids. Metalloids are elements which show properties of both metals and non-metals. Examples of metalloids are silicon, germanium, and antimony. We can classify metals and non-metals very distinctly on the basis of their physical and chemical properties. Physical properties of metals. Let us perform some activities to understand the various physical properties of metals. Take samples of metals like iron, copper, aluminium, and magnesium. Note the appearances of these samples. All of them do not look very shiny. Now, clean the sample with sandpaper and note their appearance again. All of them now have a shiny surface. This property of metals is called metallic luster. Metals in their pure state have a shine. When they are kept exposed to air for a long time, they react with oxygen and moisture in the air and lose their shine. They can be polished to regain their original shine. Take an iron nail, a thick copper wire, a thick aluminium wire, a magnesium ribbon, and metal sodium. Sodium is highly reactive, hence carefully place a piece of sodium metal on a watch glass. Now try and cut each of these metals with a knife. Which metal can be cut? Only sodium can be cut with a knife. The other metals are very hard and cannot be cut with a knife. Metals are generally hard. The hardness varies from metal to metal. Metals like iron, copper, aluminium, and magnesium cannot be cut with a knife. Alkali metals like sodium and potassium are soft metals and therefore can be easily cut. Take three objects like a bottle lid, a coin, and a thick aluminium wire. Strike them with a hammer several times. What do you observe? Do any of the objects break or get deformed? Well, the bottle lid is bent. The coin and the aluminium wire have flattened. But none of these objects are broken. This leads us to infer that metals can be flattened to form thin sheets. This property of metals is called malleability. You might have noticed the fine zari border on silk saris. Have you ever wondered what the zari is made up of? Zari is made of fine silver thread or fine silver thread coated with gold. How is it possible to make such intricate designs using zari? This is possible because gold and silver can be drawn or stretched into fine threads. You might have also observed delicate and intricate designs on gold and silver ornaments. Now try this activity. Take a connecting wire and remove its insulation. What do you observe? There are thin copper wires inside it. From these observations, we can say that metals like copper, gold, and silver can be drawn into wires. The property by virtue of which metals can be drawn into thin wires is called ductility. Gold, silver, and aluminium are highly ductile metals. It has been found that 1 gram of gold can be drawn into a wire which has a length of approximately 2 kilometers. Can you name some metals that are used to make vessels of cooking? Aluminium, copper, and stainless steel are mostly used to make cooking vessels. Stainless steel is not a pure metal, but is an alloy of iron, carbon, chromium, and nickel. Why are these metals used to make cooking vessels? Let us perform an activity to explore this. Take a thick aluminium wire or copper wire and clamp it on a stand. Skew or place a wedge of butter or wax on the free end of the wire. Heat the other end of the wire using a burner. Do you find a change in the piece of butter or wax? Yes, the butter or wax has melted. This happened because heat was conducted through the wire. Has the metal wire melted? No, the metal wire is intact because metals have a high melting point. We can conclude that metals are good conductors of heat. It has been found that metals like copper, silver, and aluminium are good conductors of heat. However, lead and mercury are poor conductors of heat. Can metals conduct electricity also? Let us perform an activity to understand this. Let us first set up an electrical circuit using a battery, bulb, switch, connecting wires, and crocodile clips. Insert a copper foil between the ends of the crocodile clips. Now, switch on the current. What do you observe? The bulb glows. This shows that the copper foil can conduct electricity. Do you know what material is generally used in an electric wire? Electric wires are made of copper and are coated with an insulating material. Copper is a good conductor of electricity. This insulating material is polyvinyl chloride, that is PVC, which is a bad conductor of electricity. We can conclude that metals are good conductors of electricity. Silver, copper, gold, aluminium are good conductors of electricity. The next physical property of metals is their melting point and boiling point. Metals usually have a high melting point and boiling point except for sodium and potassium, which have very low melting and boiling points. Tungsten has the highest melting point, while gallium and cesium melt at room temperature. Metals are sonorous. They produce a ringing sound when they are hit with a hard surface. Due to this property, metals are used for making bells in schools, temples, and churches. Now, let us summarize the physical properties of metals. Physical state. Most metals are in the solid state. Exceptions are mercury and gallium, which are in the liquid state. Luster. Metals have a metallic luster. Malleability and ductility. Metals are malleable and ductile. Hardness. Metals are hard. Exceptions are sodium and potassium. Melting and boiling points. Metals usually have high melting and boiling points. Sodium and potassium are exceptions. Conduction of heat and electricity. Metals are good conductors of heat and electricity. Physical properties of non-metals. Let us perform all the activities done earlier on some non-metals to know the difference between the two. Take samples of coal, graphite, sulfur and iodine. First we shall check for luster. Do any of the samples have luster? Coal and sulfur do not have luster. Graphite and iodine have a lustrous appearance. Next property is the malleability, ductility and hardness. Hammer the pieces of coal, graphite, sulfur and iodine. What do you observe? All these samples break easily when hammered. They are brittle. Conduction of electricity and heat. Arrange a circuit. Place the sample of graphite within the circuit. Switch on the current. What do you observe? The bulb glows. Now, place the sample of sulfur within the circuit. Does the bulb glow? No, the bulb does not glow when sulfur is inserted in the circuit. This shows that graphite conducts electricity while sulfur does not. Similarly, iodine too does not conduct electricity. In the same way, most non-metals do not conduct heat. Physical state. Non-metals are either in the solid state or the gaseous state. Bromine is an exception. It exists in the liquid state. Luster. Non-metals do not have luster. Graphite and diamond, which are allotropes of carbon, are exceptions. Iodine is also an exception. They all have luster. Malleability and ductility. Non-metals are neither malleable nor ductile. Hardness. Most solid nonmetals are soft. Carbon in the form of diamond is an exception. It is extremely hard. Melting and boiling points. Nonmetals have very low melting and boiling points. Diamond is an exception. It has a high melting and boiling point. Conduction of heat and electricity. Nonmetals do not conduct heat and electricity. Graphite, an allotrope of carbon, is an exception. It can conduct electricity. Differentiating metals from nonmetals. Elements can be classified more clearly into metals and nonmetals on the basis of their chemical properties. Let us begin with an activity to differentiate between metals and nonmetals based on their chemical properties. Heat a magnesium wire. What do you observe? The magnesium wire burns vigorously in air, producing a bright light and a white powder of magnesium oxide. Dissolve the white powder in water. The white powder formed in the case of magnesium wire is partially soluble in water. Magnesium oxide dissolves partially in water to form magnesium hydroxide solution. If a blue litmus paper and a red litmus paper is dipped in a solution of magnesium hydroxide, the blue litmus paper does not show any change in color. But the red litmus paper changes from red to blue. This shows that magnesium oxide is basic in nature. Most of the metal oxides are basic in nature.
Take some sulfur powder in a deflagrating spoon. Now, place it over a burner and heat it. What do we see? The sulfur is burning. Place the spoon in a gas jar quickly and close it with a lid. Do you notice any change inside the jar? A gas gets collected in the gas jar. This gas is sulfur dioxide. It is formed from the chemical combination of sulfur and oxygen. Now, open the jar containing sulfur dioxide. Remove the spoon from the jar and add 20 to 25 milliliters of water into the jar. The sulfur dioxide gas dissolves in the water and we get a solution of sulfurous acid. Now, place both red and blue litmus papers in the jar containing sulfurous acid solution. The red litmus remains red and the blue litmus changes to red. This shows that the oxide of the nonmetal sulfur is acidic. Usually oxides of nonmetals are acidic. By dissolving oxides of nonmetals in water, we can form acids.
Chemical properties of metals. Reaction with air. Take a copper wire, an aluminium wire, a magnesium wire, and a piece of sodium. Let us heat all the metals one by one. Let us begin with copper wire. Hold a copper wire with a pair of tongs, heat it over the flame. What do you observe? There is no change in the copper wire. Heat it for a longer time. Now we see that a black layer of copper oxide is formed over the wire. Next, heat an aluminium wire. What do we see? There is a white layer of aluminium oxide formed over the wire. Now heat a magnesium wire. What do you observe? The magnesium wire burns vigorously in air, producing a bright light and a white powder of magnesium oxide. Next is sodium metal. It reacts with oxygen even at room temperature because sodium is highly reactive. Thus, sodium is stored in kerosene to prevent its reaction with oxygen, moisture and carbon dioxide in air. Let us now check whether the metal oxide formed is soluble in water. We shall begin with copper. Carefully transfer the black product formed on the copper wire in water. Is it soluble? No, it is not. Similarly, check in the case of aluminium and magnesium. What do you observe? The white layer formed on the aluminium wire is insoluble in water. The white powder formed in the case of magnesium wire is partially soluble in water. Let us now summarize the reactions of metals with oxygen. Reaction of metals with oxygen. We have seen that most metals react with oxygen to form metal oxides. Copper, on heating for a long time in air, forms a black layer of copper oxide. Copper is the least reactive of all these metals. Aluminium reacts with oxygen in air to form a thin layer of aluminium oxide. It is less reactive than magnesium. Magnesium does not react with oxygen at room temperature. On heating, magnesium reacts with oxygen in air and burns vigorously, producing intense heat and light to form a white powder of magnesium oxide. Sodium and potassium are highly reactive metals. They react with oxygen even at room temperature. Sodium reacts with oxygen to form sodium oxide. Potassium also reacts with oxygen to form potassium oxide. Let us discuss the reactivity of some other metals with oxygen. Iron does not burn in air even on strong heating. When iron filings are sprinkled on the burner, they react with oxygen in air and burn vigorously to form iron oxide. Zinc burns in air only on strong heating and reacts with oxygen to form zinc oxide. Metals also give distinct colored flames when heated. The color of the flame is unique to the metal heated. For example, copper gives a bluish-green flame when heated. Similarly, sodium gives a bright yellow flame and potassium gives a lilac-colored flame. Iron burns with a golden flame while zinc burns with a colorless flame. It is observed that even at ordinary temperature, metals like aluminium, when exposed to air for a long time, develop a layer of oxide on them. This layer protects the metal surface underneath it from corrosion. One such process of forming a layer of oxide on the surface of aluminium metal is called anodizing. In this technique, the electrolyte used is dilute sulfuric acid. The aluminium article is used as an anode and a carbon rod is used as the cathode. This technique is an application of electrolysis. During electrolysis, oxygen, which is produced at the anode, combines with aluminium, resulting in the formation of a black thin film of aluminium oxide on the surface of the anode. If a colored dye is used during electrolysis, the oxide layer that is formed traps the dye and gives a colored surface to the metal. Thus, the aluminium article gets a colored surface with a decorative finish. It makes the aluminium surface resistant to corrosion and abrasion. Kitchen articles like anodized pressure cooker, anodized pans, and frames of sliding windows are the applications of anodizing technique. Reaction with water. Take samples of sodium, calcium, magnesium, iron, and zinc. We shall now carefully add each of these metals separately in cold water and observe the reactions. Let us begin with sodium. Sodium metal reacts vigorously with water, producing sodium hydroxide and hydrogen gas. The hydrogen gas evolved catches fire. A lot of heat is produced, hence it is an exothermic reaction. Another metal which can produce a similar reaction is potassium. Potassium reacts vigorously with water, producing potassium hydroxide and hydrogen gas. How does calcium react? Calcium reacts with water less vigorously, producing bubbles of a gas which stick to the surface of the metal. This causes the metal to float in the water. Calcium forms calcium hydroxide and hydrogen gas is evolved. The heat evolved in this reaction is not sufficient for the hydrogen gas to catch fire. Now let us check what happens when an iron nail, a magnesium ribbon, an aluminium wire, and a piece of zinc metal is put in cold water. What do you see? Iron, zinc, magnesium, and aluminium do not react with cold water. Now let us see whether these metals, that is iron, magnesium, aluminium, and zinc, react with hot water. Iron, aluminium, and zinc do not react with hot water. Magnesium reacts with hot water to produce magnesium hydroxide and hydrogen gas. The metal starts floating in water due to the bubbles of hydrogen gas sticking to the metal surface. Do the metals iron, aluminium, and zinc react with steam? To find this out, let us perform an experiment using the metal iron. In a boiling tube, place a piece of glass wool soaked in water at the base of the tube. Place the piece of iron in the middle of the boiling tube. On heating the boiling tube, water gets converted to steam, which reacts with iron to form iron oxide and hydrogen gas. Hydrogen gas comes out of the boiling tube and is collected over water in a gas jar. This experiment shows that iron reacts with steam. Similarly, aluminium and zinc also react with steam to form the corresponding metal oxide and hydrogen gas. Aluminium forms aluminium oxide and hydrogen gas, while zinc forms zinc oxide and hydrogen gas. Metals like copper, lead, gold, and silver do not react with cold or hot water or even steam. Reaction with acids. Take samples of magnesium, aluminium, zinc, iron, and copper in separate test tubes. Add dilute hydrochloric acid to each of the test tubes and observe. In all the test tubes, there is evolution of a gas in the form of bubbles except for the test tube containing copper. What is the reaction? The metals react with acid to form the metal chloride and hydrogen gas. Is the rate of formation of bubbles the same in all the test tubes? No, it is not the same. In the test tube containing magnesium, the rate of bubbling is fast, followed by aluminium, then zinc, and the last is iron. So we can say that magnesium is more reactive than aluminium, followed by zinc and then iron. Let us see the reactions. Magnesium reacts rapidly with dilute hydrochloric acid to form magnesium chloride and hydrogen gas. Aluminium reacts slowly with dilute hydrochloric acid compared to magnesium. to form aluminium chloride and hydrogen gas. The reaction between zinc and dilute acid is less rapid than aluminium. The products formed are zinc chloride and hydrogen gas. Iron reacts very slowly with dilute hydrochloric acid to form iron chloride and hydrogen gas. Copper does not react with dilute hydrochloric acid. Now, let us discuss the reactivity of these metals with dilute sulfuric acid. Metals react with sulfuric acid to form the metal sulfate and hydrogen gas. Iron reacts with sulfuric acid to form ferrous sulfate or iron sulfate and hydrogen gas. Zinc reacts with the sulfuric acid to form zinc sulfate and hydrogen gas. Similarly, magnesium also reacts with sulfuric acid to form magnesium sulfate and hydrogen gas. How do these metals react with dilute nitric acid? When a metal reacts with dilute nitric acid, hydrogen gas is not evolved. This is because nitric acid, being a strong oxidizing agent, oxidizes the hydrogen produced into water, and nitric acid itself gets reduced to any of the nitrogen oxides, that is, nitrous oxide, nitric oxide, or nitrogen dioxide. For example, copper reacts with dilute nitric acid to give copper nitrate, water, and nitric oxide. Copper reacts with cold and concentrated nitric acid to give copper nitrate, water, and nitrogen dioxide. Zinc reacts with dilute nitric acid to form zinc nitrate, water, and nitrous oxide. But metals like magnesium and manganese react with cold and very dilute nitric acid to form the metal nitrate and hydrogen gas. Magnesium reacts with dilute nitric acid to form magnesium nitrate and hydrogen gas. Manganese reacts with dilute nitric acid to form manganese nitrate and hydrogen gas. We know that gold and platinum do not react with water or any acids. They can be dissolved in a highly corrosive and fuming liquid called aqua regia. Aqua regia is a freshly prepared mixture of 3 parts of concentrated hydrochloric acid and 1 part of concentrated nitric acid, the ratio being 3:1. Reaction with solutions of other metal salts. Take solutions of copper sulfate and magnesium chloride in 2 test tubes. Put an iron nail in the solution of copper sulfate and a copper wire in the solution of magnesium chloride. Do you find any change in the iron nail? The iron nail gets coated with a reddish-brown color, and the blue color of the copper sulfate solution has faded. What must be the reaction? Iron displaces copper from copper sulfate solution to form iron sulfate and copper. It is this copper which gets coated on the iron nail. This is a displacement reaction. Why does iron displace copper from the solution? Iron, being more reactive than copper, displaces it. Thus, we can say that A, which is the more reactive metal, can displace a less reactive metal B from the salt solution. In the second test tube, is there any change in the copper wire? No, there is no change in the copper wire. This is because Copper is less reactive than magnesium, so it cannot displace magnesium from its salt. What would happen if a copper coin is dipped in a solution of silver nitrate? The copper coin gets a shiny coat of silver and the solution becomes blue due to the formation of copper nitrate. Copper, being more reactive than silver, displaces it. The activity series. All metals are not equally active. Some of them are more active, while others are less active. Metals which can easily donate electrons to gain positive charge are active metals, while less active metals do not lose electrons easily. Activity of metals is compared with oxygen, water, and acid. As all elements do not react with these reagents, substitution reactions are used to measure activity of metals. More reactive metals can displace less reactive metals from their salt solution. When a zinc metal piece is placed into CuSO4 solution, more active zinc metal will displace less active copper from copper sulfate solution. As a result, blue color of copper sulfate disappears. Reddish-brown particles of copper get collected at the bottom of the vessel. Solid zinc displaces copper from aqueous CuSO4 to form aqueous ZnSO4 and copper metal. But less reactive copper metal, when added to zinc sulfate solution, no chemical reaction occurs to release any metal. Thus, zinc is more reactive than copper. From experimental results, metals can be arranged in descending order of their activity, which is known as activity series of metals. Metals on left-hand side of hydrogen are more reactive than those on right-hand side of hydrogen. Thus, potassium is the most reactive metal in this series, followed by sodium, calcium, magnesium, aluminium, and so on. While gold is the least reactive. Take 3 test tubes and give them numbers 1, 2, and 3. Take 0.1 gram ferrous sulfate, 0.1 gram copper sulfate, and 0.1 gram silver nitrate in the test tubes 1, 2, and 3 respectively. Add 10 ml of distilled water to each test tube and dissolve the salts in it. Keep a piece of zinc metal, iron nail or screw, and a piece of copper wire. Now, add the piece of zinc metal to test tube 1, the iron nail or screw in test tube 2, and the piece of copper wire to test tube 3. Place the 3 test tubes in order in a test tube stand and observe the solutions and metal in each test tube. After approximately 5 minutes, you will observe that the metal from the solution gets deposited on the metal which is added to the test tube. After half an hour, we will observe that in test tube 1, the shiny piece of zinc metal possesses the color of iron due to deposition of iron metal on it. In test tube 2, the nail or screw will appear brown colored due to deposition of copper on it. In test tube 3, silver is deposited on the wire of copper, and due to this, copper appears shining white in color. After half hour, the color of the solution in test tube 1 would have changed from light green to colorless. In test tube 2, the solution would have changed from light blue to light green, and that in test tube 3 would have changed from colorless to light blue. We see that Fe is displaced from solution of FeSO4 by Zn So Zn is more active metal than Fe. Similarly, Cu is displaced from solution of CuSO4 by metal Fe, so Fe is more active metal than Cu. And Ag is displaced from solution of AgNO3 by Cu metal, so Cu is more active metal than Ag. Thus, the order of activity of all the four metals will be Zn greater than Fe, greater than Cu, greater than Ag. Reaction of metals with non-metals. We know that noble gases like neon and argon have a complete valence shell, hence they are not reactive. The reactivity of elements depends upon the tendency of an atom to attain a complete valence shell. Let us discuss the electronic configurations of some elements to help us to understand their reactivity and formation of different compounds. Sodium symbol Na, atomic number 11. There are 2 electrons in the K shell, 8 in the L shell, and 1 in the M shell. Magnesium Mg, atomic number 12, 2 electrons in the K shell, 8 in the L shell, and 2 in the M shell. Aluminium Al, atomic number 13, 2 electrons in the K shell, 8 in the L shell, and 3 in the M shell. Potassium K, atomic number 19, 2 electrons in the K shell, 8 in the L shell, 8 in the M shell, and 1 in the N shell. Calcium Ca, atomic number 20, 2 electrons in the K shell, 8 in the L shell, 8 in the M shell, and 2 in the N shell. Nitrogen symbol N, atomic number 7. There are 2 electrons in the K shell and 5 in the L shell. Oxygen symbol O, atomic number 8, 2 electrons in the K shell and 6 in the L shell. Fluorine F, atomic number 9, 2 electrons in the K shell and 7 in the L shell. Phosphorus P, atomic number 15, 2 electrons in the K shell, 8 in the L shell, and 5 in the M shell. Sulfur S, atomic number 16, 2 electrons in the K shell, 8 in the L shell, and 6 in the M shell. Chlorine Cl, atomic number 17, 2 electrons in the K shell, 8 in the L shell, and 7 in the M shell. Now let us concentrate only on the 2 elements sodium and chlorine. Sodium is a silver-colored metal. It reacts violently with water to produce hydrogen gas. This hydrogen gas immediately catches fire. Chlorine, which is a non-metal, is a greenish-yellow-colored poisonous gas. It was used as a chemical weapon in World War I. Both these are dangerous substances, but when they are brought together, how do they form common salt that is so safe to eat? Let us discuss the formation of sodium chloride. Formation of sodium chloride. We know that the electronic configuration of sodium atom is 281. If sodium atom loses its 1 electron from the M shell to attain a stable octet, then its L shell will become its outermost shell. The sodium atom now has 11 protons in its nucleus, but the number of electrons is 10. This leads to the formation of a positively charged sodium cation. On the other hand, chlorine atom has 7 electrons in its outermost shell. It requires 1 more electron to complete its octet. The electron lost by the sodium atom is accepted by the chlorine atom. Now the number of electrons in the chlorine atom is 18, but the number of protons is still 17. This leads to the formation of negatively charged chloride anion. Sodium ions and chloride ions are opposite in charge and therefore experience a strong attraction for each other, so they remain tightly held together, forming an ionic or electrovalent bond. This results in the formation of the compound sodium chloride. Sodium chloride consists of a large aggregate of an equal number of sodium ions and chloride ions arranged in a definite geometrical shape. Let us define an ionic bond or an electrovalent bond. A chemical bond formed by the transfer of electron or electrons from one atom to another atom, or formed by a give and take of electrons, is known as an ionic or electrovalent bond. The atom that loses electrons becomes positively charged, and the atom which gains electrons becomes negatively charged. These oppositely charged ions are attracted to each other by strong electrostatic forces, and an ionic bond is formed. From the above example, we can now say that ionic bonds are formed between metals and non-metals. Compounds formed by the transfer of electrons from a metal to a non-metal are known as ionic or electrovalent compounds. Formation of magnesium chloride. The electronic configuration of magnesium atom is 2-8-2. Magnesium loses its 2 electrons from the M shell to form a magnesium ion. Since a chlorine atom has 7 electrons in its outermost shell, it requires 1 more electron to complete its octet. In the formation of a magnesium chloride molecule, the 2 electrons lost by the magnesium atom are accepted by the 2 chlorine atoms. This leads to the formation of 2 chloride ions. Magnesium ions and chloride ions are held together by an ionic or electrovalent bond. This results in the formation of the compound magnesium chloride. A simpler way to understand the formation of salts is by their dot structures. Consider sodium chloride. It consists of 1 atom each of sodium and chlorine. The single valence electron of sodium is represented by a dot. The 7 valence electrons of chlorine are represented by crosses. The single valence electron of sodium is accepted by chlorine to form sodium chloride. Similarly, in the case of magnesium chloride, the 2 valence electrons are represented by 2 dots. These 2 electrons are accepted by 2 chlorine atoms, and this results in the formation of magnesium chloride. Properties of ionic compounds. Take samples of sodium chloride, potassium iodide and barium chloride. What is the physical state of these salts? They are all crystalline solids. Now let us take each of these samples one by one on a metal spatula and observe the changes taking place when they are heated on a burner. We shall begin with sodium chloride. Heat sodium chloride. What do you observe? Sodium chloride does not melt easily. On heating strongly, it melts and gets converted to the liquid state. Potassium iodide and barium chloride also melt after prolonged heating. Now let us check the solubilities of each of these samples, first in water, then in petrol, and finally in kerosene. Sodium chloride, potassium iodide and barium chloride are all soluble in water. All the 3 salts are insoluble in petrol. Now let us see whether they are soluble in kerosene. All the 3 salts are insoluble even in kerosene. Now let us determine whether the solutions of these salts conduct electricity. Prepare an electrolytic cell by connecting the carbon rods or electrodes to the positive and negative terminal of the battery. Connect a bulb in the circuit. Insert the electrodes in the solution of sodium chloride. Switch on the current. What do you observe? The bulb glows. Let us check the same for the other solutions. The bulb glows when each of the other salt solutions is used. This shows that all these solutions can conduct electricity. General properties of ionic compounds. Ionic compounds exist in the solid state because the positively and negatively charged ions are held together by a strong force of attraction. This also makes them hard and brittle. Ionic compounds have high melting and boiling points. This is because a considerable amount of energy is required to break the strong forces of attraction between the oppositely charged ions. Ionic compounds are soluble in water and insoluble in organic solvents like petrol, kerosene, and benzene. Solid ionic compounds do not conduct electricity because the ions in them are not free to conduct electricity. When these compounds are dissolved in water or when they are melted, the ions become free to move and can conduct electricity. Occurrence of metals. Metals occur in nature, in the free state and in the combined state. Unreactive metals like gold, silver and platinum occur in the free state. Most of the other metals usually occur in the combined state as their oxides, carbonate or sulfides. Natural materials in which compounds of metals occur along with other impurities are called minerals. What are ores? Minerals from which metals can be extracted profitably are called ores. After the ore is mined, it has to be converted to the pure metal. The process of obtaining a metal from its ore is called extraction. The processes which involve the extraction of metals from their ores and their refining are known as metallurgy. The processes used for the extraction of metals depend upon their reactivity. Metals can be arranged in the order of their decreasing reactivity. Such an arrangement is called the activity series. Extraction of metals. Metals like potassium, sodium, calcium, magnesium and aluminium are highly reactive, so they are placed at the top of the activity series. Zinc, iron and lead are metals of medium reactivity and copper, mercury, silver and gold are the least reactive metals. The step in the extraction of a metal from its ore are enrichment of the ore, followed by the actual extraction of the metal and finally refining of the metal. Enrichment of the ores. Along with metals, ores also contain certain impurities like sand, rocky material, earthy particles, etc. These impurities are called gangue. Gangue is mainly composed of silicon dioxide, also called as silica. Before extracting the metal from its ore, it is necessary to remove the impurities or gangue from the ore. By removing the gangue from the ore, we get an ore containing a higher percentage of the metal. This process is called concentration of the ore or enrichment of the ore. Methods of extracting metals on the basis of their position in the activity series. Extraction of metals low in activity series. Metals placed at the bottom of the activity series are the least reactive. For example, copper, mercury, silver and gold. These metals can be extracted from their oxide or sulfide ore by just heating them in air. Copper is found as copper sulfide in its ore, copper glance. When the copper sulfide ore is heated in air, part of the copper sulfide is oxidized to copper oxide. Sulfur dioxide is also formed in the reaction. When the supply of air for heating is stopped, the copper oxide formed earlier reacts with the copper sulfide to form copper metal and sulfur dioxide. Similarly, mercury is obtained from its ore, cinnabar. When the ore is heated in air, mercury sulfide is first converted to mercury oxide and sulfur dioxide. When this mercury oxide is further heated, it gets reduced to mercury. Extraction of metals with medium reactivity. Metals placed in the middle of the activity series, that is zinc, iron and lead, are moderately reactive. These metals are usually present in the form of their sulfides or carbonates. It is easier to obtain a metal from its metal oxide by reduction than from its metal sulfides or metal carbonates. Therefore, metal sulfides or metal carbonates are first converted to metal oxides by processes like roasting or calcination. Roasting and calcination. Roasting. In this method, the sulfide ore is heated strongly in the presence of excess of air to convert it into oxide. For example, zinc occurs in the form of zinc sulfide in its ore, zinc blende. Zinc sulfide, when heated strongly in the presence of air, can be converted to zinc oxide. Carbonate ores can be converted to metal oxides by a process known as calcination. In this method, the carbonate ore is heated strongly in the presence of limited supply of air. Zinc also occurs as zinc carbonate in its ore, calamine. Zinc carbonate, when heated strongly in the presence of limited supply of air, gets converted to zinc oxide. The metal oxide so obtained by calcination or roasting is reduced to zinc by reducing agents like carbon. Besides carbon, highly reactive metals like sodium, calcium and aluminium are used as reducing agents to extract metals of comparatively lower reactivity. For example, manganese metal is obtained from its oxide by using aluminium powder as a reducing agent. In this reaction, aluminium is oxidized to aluminium oxide and manganese dioxide is reduced to manganese. It is an exothermic reaction and the metal manganese produced is in the molten state. This is also a displacement reaction in which manganese is displaced by aluminium. The such type of reaction using aluminium as a reducing agent is the thermite reaction. Here, iron oxide is reduced by aluminium powder to produce the metal iron in the molten state. This property of reduction of aluminium is used in thermite welding for joining broken pieces of railway tracks. Extraction of metals of high reactivity. Metals placed on the top of the reactivity series are highly reactive. For example, potassium, sodium, calcium, and aluminium. These metals occur in the form of their oxides or chlorides. These metals have a strong affinity for oxygen than for carbon. Therefore, they cannot be extracted by reducing their oxides with carbon. Hence, the process of electrolytic reduction is used to obtain the metal from the metal oxide or the metal chloride. The metals sodium, potassium and calcium are obtained by the electrolysis of their molten chlorides. In this process, the pure metal is obtained at the cathode and chlorine gas is obtained at the anode. For example, in the electrolysis of molten sodium chloride, sodium metal is obtained at the cathode and chlorine gas at the anode. In the electrolysis of magnesium chloride, magnesium metal is obtained at the cathode and chlorine gas is obtained at the anode. In the electrolysis of calcium chloride, calcium metal is obtained at the cathode and chlorine gas is obtained at the anode. Similarly, aluminium is also obtained by the process of electrolytic reduction of its oxide. Let us understand the extraction process of aluminium metal in detail. Extraction of aluminium. Aluminium is a silvery white metal. Its symbol is Al and it belongs to group 13 of the periodic table. Its atomic number is 13 with electronic configuration 283. Aluminium shows a fixed valency of 3 in its compounds. Aluminium is a reactive metal. It occurs as an oxide in nature. The most important and common ore of aluminium is bauxite, which is hydrated aluminium oxide, Al2O3H2O. The ore contains about 30 to 70% of aluminium oxide. The remaining portion is gangue, which is made up of sand, that is, silicon dioxide and iron oxide. Iron oxide gives the ore its brown-red color. The extraction of aluminium involves 2 steps. The first step is the concentration of the ore and the second step is the electrolytic reduction of pure alumina. Concentration of the ore. We know that crude bauxite ore contains the impurities silicon dioxide and ferric oxide. The concentration of the ore involves the removal of these impurities and conversion of bauxite to pure aluminium oxide or alumina. This process is called Bayer's process. In this method, the bauxite ore is first crushed and treated with hot sodium hydroxide or caustic soda under high pressure for about 2 to 8 hours and a temperature of about 140 to 150 degrees Celsius, and is carried out in a tank called a digester. Aluminium oxide of the bauxite ore is amphoteric in nature, that is, it can react with an acid as well as a base to form salt and water. It therefore reacts with aqueous sodium hydroxide and dissolves in it to form water-soluble sodium aluminate. Electrolytic reduction of alumina. Electrolytic reduction or electrolysis is carried out in a large steel tank which has a graphite lining on the inner side. This lining acts as the cathode. There is a set of carbon rods or graphite rods dipped in the molten electrolyte, that is, alumina, which act as anode. Pure alumina has a high melting point which is greater than 2000 degrees centigrade. In order to lower the melting point, pure alumina is mixed with molten cryolite Na3Alf6 and fluorspar CaF2 and then melted in the steel tank. Thus, electrolysis can be carried out at about 1000 degrees Celsius. Now let us see the reactions taking place during the electrolysis of alumina. On passing the electric current, electrolysis of alumina takes place. During electrolysis, the negatively charged oxide ions are attracted to the anode. Here they lose electrons to form oxygen gas. The positive aluminium ions are attracted to the cathode. Here they gain electrons to form the molten aluminium metal. Molten aluminium is denser than the electrolytic mixture of alumina, cryolite and fluorspar, hence is collected at the bottom of the tank. It has to be removed from time to time. Oxygen gas liberated at the anode has a tendency to react with the carbon anode itself to form carbon dioxide gas. So the carbon anodes are gradually oxidized or consumed during the electrolysis, and therefore they have to be replaced from time to time. Metals obtained after reduction processes may contain impurities. The process of purifying impure metals is called refining. Refining of the metals. The most widely used method of refining metals is electrolytic refining. In this process, the impure metal is connected at the positive terminal of the battery and a thin strip of pure metal is connected at the negative terminal. The water-soluble salt of the metal to be refined is taken as the electrolyte. On passing electric current, the impure metal dissolves from the anode and goes into the electrolyte. The metal from the electrolyte deposits on the cathode. The soluble impurities present in the impure metal go to the solution, whereas the insoluble impurities settle down at the bottom of the anode. In this way, the pure metal is produced at the cathode. Consider the electrolytic refining of copper. The electrolyte taken is a solution of pure acidified copper sulfate. Pure copper metal is taken as the cathode or the negative electrode, while an impure strip of copper is taken as the anode, which is positive electrode. When electric current is passed, copper from anode goes into the solution, while an equivalent quantity of copper ions from the electrolyte gets deposited on the cathode. In this manner, pure copper is obtained at the cathode. Corrosion. What is corrosion of metals? You must have observed that iron objects, if remained unused for some time, get rusted. This process is called corrosion. The major problem of corrosion occurs with iron because it is used as a structural material in constructions, shipbuilding and cars, etc. The degradation of a metal by the action of air, moisture or acids is called corrosion. When an iron object corrodes, a red-brown layer is formed on the metal surface. This is called rust. Copper objects also lose their shine when exposed to damp air for a long time. Copper reacts slowly with the carbon dioxide and water from the air to form a green coating. This coat is actually a mixture of copper carbonate and copper hydroxide. Therefore, it is basic in nature. When such corroded copper vessels are rubbed with substances like tamarind or lime, the acid present in them dissolves the green-colored basic copper carbonate. This makes the copper vessel regain its shine. When silver articles are exposed to air, they lose their shine and become black. This is because silver reacts with the compounds of sulfur, such as hydrogen sulfide, and forms a black coat of silver sulfide. Aluminium metal begins to corrode quickly when it comes in contact with moist air. It reacts with the moist air to form a layer of aluminium oxide on the aluminium. This layer of aluminium oxide actually forms a barrier and protects the aluminium object from further oxidation. If this layer is made thicker, then the aluminium object can be protected from corrosion even more effectively.
Let us perform an activity to understand the conditions necessary for corrosion of iron. Take 3 test tubes and place 3 iron nails in each of them. Name the 3 test tubes as A, B and C. Pour water in the test tube A in such a manner that half part of nails sink in water, and then close the test tube with a cork. Add boiled distilled water in test tube B so that the nails sink completely, and add about 1 milliliter oil. Close this test tube with a cork. In test tube C, add some anhydrous calcium chloride. By doing this, the nails in test tube A are in contact with both air and water. In test tube B, the nails are in contact with water only. They do not get air. In test tube C, anhydrous calcium chloride is present, which is a moisture-absorbing substance, and so only dry air is present in test tube C. Observe the nails in all the 3 test tubes after some days. On observation, we will find that nails in test tube A are corroded, but nails in test tubes B and C are not corroded. This indicates that corrosion of metals takes place due to contact with both air and water.
Prevention of corrosion. Corrosion can be prevented if the contact between the metal surface and oxygen or moisture is cut off. The most common method of preventing corrosion is to coat the metal surface with paint, varnish, grease or oil. Corrosion of metals can also be prevented by using methods of coating a corrosive metal with a non-corrosive metal. Let us discuss some of these methods. Rusting of iron can be prevented by coating the surface of iron or steel by zinc, because zinc does not corrode on exposure to damp air. This process is called galvanization. For example, iron nails, pins and iron pipes are galvanized to prevent them from rusting. Tinning is another method used to prevent corrosion. Cooking vessels made of copper or brass often develop a greenish coating over them due to corrosion. This layer is poisonous. If copper or brass vessels are coated with a layer of tin, the vessels can be protected from corroding. Metals like copper and aluminium can be coated with a thin, strong film of oxide on them by the process of electrolysis. This oxide film protects the metal surface from further oxidation. Anodizing is one such technique used for this purpose. We are familiar with gold-plated jewelry and silver-plated articles. This is done by a process called electroplating, where a metal surface is plated by another metal by the process of electrolysis. Iron or steel articles can also be electroplated by chromium or nickel to protect them from corrosion. Alloying is another method that is used to prevent corrosion. An alloy is a homogeneous mixture of 2 or more metals or a metal and a non-metal. Stainless steel is an alloy of iron with nickel, chromium and carbon. Brass is an alloy of copper and zinc, and bronze is an alloy of copper and tin. If in an alloy one of the metals is mercury, then the alloy is called an amalgam. For example, a solution of sodium metal in mercury metal is called sodium amalgam. Solder is an alloy of lead and tin. Solder has a low melting point, so it is used for soldering of electrical wires together. What are the alloys of gold? Gold is alloyed with small amounts of silver or copper to make it hard and suitable for making intricate designs. Pure gold is said to be 24 carats. It is soft and hence not suitable to make jewelry. Generally in India, gold ornaments are made using 22-carat gold, which contains 22 parts of gold and 2 parts of copper or silver.